So, in the previous lecture, we had discussed about interior points and we further had a conversation about open sets. Till now, we have already learnt about what we call intervals, right? So, let's just recapitulate what we had studied. So, we had studied about intervals, right? So, we had two types of intervals, finite intervals and infinite. Acha, first thing which we are going to talk about in this lecture is the difference between an interval and a set. Got it? So carefully notice this. Suppose we have this interval 2 comma 5, clear, and we have a set S which has x, or let's say this is a finite interval. Let us talk about this. This is a finite interval, okay, and we also have things called finite sets, right? Finite sets. So let's say we have a finite set 2, 3, 4, 5. Now this is pretty easy to see that there are only 4 members to this set being finite. But are there only finite number of members in this finite interval? That's the difference. See, this interval is said to be finite. The reason being that this acts as a subpart or a subset of R. This acts as a subset of R. And there are infinite members in this interval. The reason being, between 2 and 5 there are infinite real numbers, and this interval always tends to represent the real number sets. Okay. So this interval has infinite members, though we call it finite. The reason being, it is bounded in both sides. It is guarded by real numbers on both sides. Getting my point? See, if we had interval of this sort 2 comma infinity, then it is guarded only on one side, but the other side is moving to infinity. Clear? Though a finite interval is also having infinite elements, and infinite interval is also having infinite elements, but this infinite interval is not guarded on both the sides by real numbers. Got it? So this becomes an infinite interval, having one side guarded to infinity, or extending to infinity. Now this is called a finite interval, but a finite interval is not having only finite number of elements. Got it? It just acts as a subpart which is closed on both the sides with real numbers. But on the other hand, if we talk about finite sets, clear? So what do we have under finite sets here? So finite sets means the cardinal number of that set is finite. Okay, there are only a finite number of elements in that particular set. It is numerically equivalent to any subset of natural numbers, which is finite also. Getting my point? So this is a difference between finite interval, a finite set, or generally speaking, an interval and a set. So don't get confused between what is an interval and what is a set. Clear? Talking about limit points. Last class we have discussed about interior points, right? And from interior points we emerged into something called open set. An open set was if all its elements are the interior points of that particular set, then we used to call that set an open set. So what is a limit point? Let's see. Talking about limit points. Okay. Let us understand using an example. Let's say you have a set S. Set is a closed interval from 2 to 7. Okay. And we pick a number from this interval. Let's say 3. So 3 will belongs to this this interval itself. Clear? Now let's take an epsilon neighborhood of 3. So any general neighborhood of 3. So it is given like this, right? So x belonging to R such that mod of x minus 3 is less than epsilon for all epsilon greater than 0, right? Or on the other hand, we can write it simply as an open set 3 minus infinity to 3 plus infinity. Got it? So let's say we represent this on a number line. So we have the interval as, so this is, let's say 2, here we have 7, let's say this is the point 3. Now carefully notice that, see, since this neighborhood exists for all positive numbers represented by epsilon. So if we take any neighborhood of epsilon, suppose we say epsilon is 0.1. So what does the epsilon neighborhood becomes? 2.92, 2.92, 3.1. Suppose this is the neighborhood. Okay, this is 2.9, this is 3.1. And since this is an interval, we can easily notice that there exists some element x which belongs to S such that x also belongs to this epsilon neighborhood of 3 and x is not equal to 3. That is, there are elements other than 3. There are elements other than 3 which is mutually present in both S as well as the neighborhood of 3. Got it? Similarly, if we take any epsilon greater than 0, even if the epsilon is such that it kind of covers this whole interval we took. Suppose we take an epsilon, let's say we take epsilon as 10, let's say. So what does the interval become? V10 of 3. So this is 10 minus 3, sorry, 3 minus 10, that is minus 7, and 3 plus 10, that is 13. So the interval, basically it looks like something of this sort. Let's say we extend this number line. So we have, suppose this is your minus 7 and here we have say 13. Still, see, since this neighborhood covers this whole interval, so there are still mutual elements present in the interval as well as the neighborhood other than 3. This phrase is important. Other than 3. Is this part clear? Okay. So if such a real number exists such that you have mutual elements in some subset of R as this interval we speak and the neighborhood of that particular real number other than that number itself, then such uh, such real numbers are called limit points of the given subset of R. Mathematically speaking, nothing else here. So what we mean to say is that, okay, so if there exists some P which belongs to the set of reals such that V epsilon of P intersecting S is the subset we considered. For example, this interval 2 to 7, right? Closed interval. This minus P is not a null set. Okay, such that this is not a null set, then P is said to be a limit point, a limit point of S. Is the definition clear of limit points? Is it clear? So now the question arises that how should we choose this number to check whether it is a limit point of some given interval or not? Suppose we have a closed interval from A to B and we choose P such that P does not belong to this interval. Does not belong to this interval. One more thing, just here have here such that for all epsilon greater than 0. That is, we are talking about all neighborhoods of this particular number. All neighborhoods. Okay, not some finite number of neighborhoods. All neighborhoods possible for all positive epsilons. Now say P is not belonging to this particular interval, and you know without loss of generality, let's say without loss of generality, P is less than A. Without loss of generality, we use that we can also consider P to be greater than B. We can also consider P to be greater than B, but the whatever result, whatever conclusion which we are going to derive from P being less than A, the same thing is going to be with P greater than B. So we are considering only this much. So if P is less than B, less than A, right? So what we get, so there basically exists some epsilon greater than 0 such that, or let's say this to be delta. Let's say this to be delta. Okay. Such that A minus P is equal to that delta, right? A minus P is equal to that delta, right? For example, if we plot this on a number line, let's say, so let's say this is your A, this is your B, here is your P. So there exists some delta which is basically the distance between A and P, right? Between A and P. This is what we are talking about. Clear? This is what we are talking. So see, this is pretty easy to understand that we can choose an epsilon from anywhere between this delta. We can choose an epsilon from anywhere between this delta such that if we now form the epsilon neighborhood, then P plus epsilon will be somewhere here, P plus epsilon, and P minus epsilon will be behind that. So see, so if P minus epsilon exists here, so this neighborhood has no elements in common with this interval as well as its neighborhood. Okay, has no elements in common with this particular interval. So that basically does not satisfy the condition for P to be a limit point of this particular interval, right? Got it? So we cannot choose a particular number, a particular real number outside of a closed set, closed interval rather, closed interval, such that it can be a limit point of that closed interval. Is this portion clear? Now there arises a slight difference of this concept in case of open interval. So if we have some open interval, let's say A comma B. Now what happens? So in case of open interval, see what does this open interval basically mean? So this means a set of elements x belonging to R such that A less than x less than B. Right? This is what we mean. So basically this interval contains all those elements, all those real numbers, every single real number, starting from the smallest to the biggest possible in between this interval, greater than A and less than B. So see now, if we take the neighborhood of this A, if we take the neighborhood of this A, so what is happening here? Let's see. See, A belongs to this neighborhood. A belongs to this neighborhood, but A does not belong to this interval. But that's not our problem. The reason being key for a number to be a limit point, we must have common elements between its neighborhood and the interval, with except that particular point. So A not being a common element between the interval and its neighborhood is not a matter of fact. What matters is whether we have other numbers in the neighborhood as well as the interval, and that's possible, right? See, again, if you plot this on a number line, so this is A, this is B, and we can take any possible epsilon greater than 0 such that, so see, this will be A minus epsilon and this will be A plus epsilon. So any possible epsilon will have infinite elements common to both the interval as well as the as well. So what conclusion we derive from here is that if we have an an open interval, what is happening is that the endpoints, the extremities which is not included in the open interval, they also become, kind of become the limit point of that particular interval. Okay, got it? What I'm trying to say, is this clear? Okay, so A also becomes a limit point of this particular interval, though A and B will also be, become the same, because B will also its interval of this form, right? Neighborhood of this form. B minus epsilon, B plus epsilon. Clear? So both A and B behave as limit points, though not being included in the interval. This is a simple, exception to this concept, which we studied. Just that for something to be a limit point, you should, just first verify whether it belongs to the interval or not. Clear? This limit point is also called cluster point. So some terminology related to limit point is that limit point is also called cluster point, is also called condensation point. Condensation point is also called accumulation point. Okay, accumulation point. So you can use either of these statements to get this concept. Clear? Limit point, cluster point, condensation point, and accumulation point. Either of these terms can basically mean your limit point. Is this part clear? Now in the previous lecture we had kind of got a conclusion that if you have a limit point, if you have an interior point, so from interior point you derive a type of set which is called an open set, right? An open set has all its elements as interior points of that particular set. So similarly, from this limit point we get a closed set. Clear? We will come to that. Before understanding closed set, let us first understand what is a derived set. So derived set is pretty easy to understand. If you have some subset of R, for example this closed interval or any open interval, any subset of R, and you find all its limit points, and you form a set of those limit points, that set becomes a derived set. For example, so derived set basically, derived set. So derived set basically means that set of all limit points of some subset of R. Okay. For example, let's say, let's say you have this interval itself, right? 2 to 7. Let's say the example which we took. So 3 was a limit point of this interval. 4 would be also a limit point. 5 will also be a limit point. 6 will also be a limit point. Similarly, we can take smaller numbers, 3.5, 3.6, 2.9999991. Right. So all those elements, if we consider as a set, so 3, 1, 1 is not included here. So 2, 3, 4, 5, so on till 7. Then the smaller numbers, x belongs to this, between 2 and 3, x belongs to 3 and 4. These elements, these smaller elements, they also become the limit points, right? So this set is basically called a derived set. This set is basically called a derived set. Now, to more effectively you will understand why this concept. Suppose you have a set S which gives you a sequence, say 1 over n for all n belonging to the set of natural numbers. Clear? So what is a sequence? So we will come to sequence later, but still I am giving you a brief introduction of what is a sequence. So if you have a function, okay, if you have a function which has its domain in the set of naturals and its codomain in the set of reals, then this f is called a sequence, real sequence. Okay. If you have a function which has its any arbitrary domain but its codomain is real, then such a function is called a real valued function. Real valued function. So a real valued function having domain as the set of all naturals is called a sequence. Got it? So if we have a sequence, then finding the limit of the limit point of this particular set containing the sequence as given is just by simply putting limit n tends to infinity 1 over n I mean the any nth element of that sequence, and this is 0. This is you people have already studied it in your plus 2 level. So what is the limit point of S? So the limit point of S is 0. The limit point of S is 0. Limits are unique of any sequence. Got it? Limit points of S of this particular sequence is 0. So what will be the derived set? Derived sets are given as dash. S dash is a singleton set. Is this part clear? Sequences, you can just find the limit n tends to infinity to find the limit point of that sequence. Clear? Concept of derived set is clear. Talking about closure of a set. The closure of a set is basically the union between the set and the set of its limit point. I mean a set and its derived set. Clear? Closure of a set. So union of a set and its derived set. So basically this set 1 over n for all n belonging to the set of naturals, union 0 is closure of S. S means this set. Okay. Got it? Okay. This is often denoted as S dash or S bar. Sorry, S bar. Dash gives you derived sets. Is this point clear? A simultaneous terminology is isolated points. Okay. Is isolated points. Isolated points. So what do isolated points say? So point in a set, point in a set, if not a limit point, if not a limit point, is called an isolated point. Is called an isolated point. So if you have a set and you have a number in that particular set or a particular interval, anything, okay, a set or interval, and you find that the interval, I mean the number, is not a limit point, so that becomes the isolated point. For example, the set we just had a conversation about 1 over n. This has its limit point as 0, right? So the rest of the numbers are not limit points, so they become the isolated points. Is that part clear? What are isolated points? Now we talk about what we call the closed set. Okay, let's see. So we are covering a great number of topics. Closed set. Okay. So if you have a set S, okay, if you have a set S, so being subset of R, and all the limit points, all the limit points of S, all the limit points of S is contained in S, then such a set as S is called a closed set. Okay. So if you have a subset of R and all the limit points of S is contained in S, then such a set is called a closed set. Is this part clear? I guess this part is understood. Okay. So what we, there are a few characteristics. Let us first, get some examples. So see, for example, you have this particular mm, closed interval. Okay. See, every limit point it has is contained in it. 0 and 3 are also contained in it. Any number between 0 and 3 will also act as a limit point. So all the limit points of this particular set will be contained in it. There is no limit point outside this particular set. So this becomes a closed set. This becomes a closed set. On the other hand, if you have 0, 3 in an open interval, so 0 is a limit point of this particular interval, but 0 is not contained in this particular set. So this becomes an open set. So I mean not a closed set, sorry, not an open set, not a closed set. We cannot say if it is not open then it's closed. Okay. A closed set has its complement open. Okay, if you have a closed set R, if S is a closed set, then S complement, that is the set of reals which are not in S, is open. This is a fact, you can have this. Got it? Let us consider a few examples. From here basically you get a input. I missed to tell you at that point of moment. If you have a open interval, then its derived set is the closed interval, because 0 and 3 are also limit points, right? 0 and 3 are also limit points. So first fact about closed set is that every finite set is closed. I'm telling you the reason behind this. See, if you take any finite set, not interval. Let's say you have some a which is 1, 2, 3, and 4. This is a finite set. Then you take any real from this particular finite set, any real. Let's say 3. Okay, you find its epsilon neighborhood, so 3 minus epsilon, 3 plus epsilon. I know there is epsilon to be say 0.2. So you have 2.8 and 3.2. Is there any element common between this interval and this particular set? There is no such element. Okay. And mandatory to see that this neighborhood must be this condition must be satisfied for all epsilon greater than 0. From here what we get, that there exists no limit point of this set. So what is its derived set? A null set. And we know that a null set is a subset of every set, right? A null also say that a dash is a subset of a. That means ki the derived set is contained in a. That means ki all limit points, though null, but is contained in the set in that particular set itself. That is why a is closed. Any finite set is closed. Clear? Similarly, natural numbers, integers, all are closed. Okay. Natural numbers, integers are closed. The same concept. This is an example of a natural set itself, a subset of a natural number itself. Got it? Though natural numbers are not finite sets, but still they are closed. Because if you take epsilon to be very small, then you will have no elements common between natural numbers and that particular neighborhood, right? Are you getting my point? Null set is also closed on itself. This is also closed. The reason being key. A null set, suppose S is a null set. So what will its derived set be? It will also be a null set. Any set is a subset of itself. So null set is also a subset of itself. So S dash is contained in S. Clear. R is closed. This is a mandatory example. Set of all reals is closed. This is pretty much direct from the definition. Rational numbers are not closed. Okay. Rational numbers are closed, not closed. Because the derived set of natural numbers becomes real numbers. Okay. The derived set of rational numbers become real numbers, which is not contained in rational numbers anymore. Clear? Kind of the concept which is related with the open intervals. Kind of. Okay. Getting it? Okay. Clear? Got it? Now there is a theorem which is related with this closed set, which is pretty simple. That is, the intersection of any arbitrary family of closed set is closed. Okay. So this is the theorem. The intersection of any family of closed set, any arbitrary family of closed set is closed. I am keeping this proof as an exercise at this moment. If possible, you people do it on your own. If not possible, I will surely be providing this proof in the starting of the next lecture. So I'm keeping this lecture up to this much, guys. In the next lecture, we will be talking about connected sets and compact sets. Okay, covers, subcovers, open covers, much more. So meeting you guys in the next lecture.